Okay, this will be the second part and final part of section 9.1 for Algebra 2, finishing up with the exponential functions. This was a warm-up I had done. It was just from the textbook, actually, page 503, numbers 10 and 11. Oop, that was supposed to be a highlighter. Um, so I'm not going to take the time to do all of the details, but it's very similar to one of the other problems that we did in the homework where we're writing an equation. So just kind of a real quick rundown. They would have given you some information. They gave you, I'm assuming, they gave you one initial point here that the graph starts at, and then they gave you another point, and you were asked to come up with some sort of equation for the exponential. So with this one, again, they're going to give you 2 points, and basically we're going to throw everything into the general form here. So just like before, the initial value is the a value that came from when the x was 0, and then the other point, the 12, was the x value, and then they gave you a y value. So you can see in purple there, kind of plug those in. I wanted to go ahead and solve for b. That was the unknown piece, so we ended up dividing by the 1 million, and this ended up giving me the 1.6718 equals b to the 12th, and I would take both sides to the 1/12 power, because we needed to find out what b was. And then once we found b, we can go ahead and write the equation as you see in the box there. And then it looks like number 11 was asking you to plug in for a certain year. Okay, I don't know off the top of my head what year that was. But we plugged in some value for x, evaluated the whole thing, and got a y value. Okay, so give that one a look if you were looking for extra practice. What I want to do though is just do one other quick little thing with exponentials. I think this might help see things a little bit. Let's say you have some data that goes through 0, 1, and then it goes through 2, 4. Okay, and let's just kind of tie this into old stuff. So let's say, if you were sitting in an Algebra 1 course or pre-algebra even, and you were asked to come up with an equation that would go through those, the first thing that probably would come to mind would be that it was linear. Okay, so just to see what the linear equation would be, and then we'll kind of see, what if it's actually exponential? How would the equation differ? So this one, remember, linear is going to be based on y equals mx plus b, where m is a slope. So for our slope, it looks like we went up 1, 2, 3, and to the right 2. Let's go to the right 2. So that would give us a slope of 3 over 2. Okay, they're both positive. So 3 over 2 is our m. And then, of course, the b value is the y-intercept, so plus 1. Okay, so that would be a linear equation that went through those 2 points. Let's say, though, now that it's exponential. Okay, and see how that differs. So let's say same 2 points, 2, 4, and if it's exponential, I know that it's going to kind of be growing faster as we go. Okay, so for an exponential model, if we think something's growing exponentially, notice there's not a same slope throughout. That slope that we had from the line is not the same throughout the whole curve here. Okay, so specifically here, that slope that we had noticed through the up 3 over 2 deal from here to here and over, that's not going to be the same. If I go up 3 again and over 2, I can see my graph is actually going to be quite a bit higher than that, the y value way up there. So the exponential is going to be when things are growing not at a steady rate. That rate changes throughout because we're actually multiplying by something. So just the quick setup here, again, our general form, y equals a times b to the x. We'll think of this point, 2, 4, as the x and the y. And then the initial point was 0, 1. That's your a value there. Okay, so if we plug everything in, we're going to get something like 4 equals 1 times, again, we don't know b, I don't know what I'm multiplying by, to the second power. Okay, that was x. So 4 equals b squared. This one we can take the square root of both sides and get 2 equals b. And then we can go ahead and write our equation now that y would equal, again, we started at 1, it was getting multiplied by 2 to the x power. So in each case, the y value is doubling, okay, every time. It started at 1, the next point it would be at 2, the next point that would double to 4, the next point that would double to 8, okay, and then way up at 16. So, so hopefully that helps kind of see the difference a little bit. Okay, but the one other thing in this section we need to cover is the introduction to solving exponential equations. So if we remember an exponential equation, okay, just like an exponential function, it has a variable in the exponent. Okay, so let's take a look um, at a little property that will help us here. And basically it says if b is a positive number, okay, remember we're going to deal with positive bases. We showed in the previous video how if the base is negative, the graph kind of jumps from positive to positive, so it just doesn't really fit. um, so if b is some positive number, and let's say you have a base to a power, so b to the x, and they're telling you it equals that same base to another power, so b to the y, that's only true then if the exponents are equal. Okay, so we can use that to help us solve some equations. Let's take a look. Excuse me. So here is a equation. It has a variable in the exponent. Okay, that's something new. We haven't solved ones like that yet, at least this year. Um, so the trick is I want to be able to write both sides with the same base. And then we can use that property that we just had um, where that the exponents must be equal if the bases are equal. So I'm looking at the left side of my equation. It's 3 to the 3x. So the base is 3. So is there a way to rewrite 27 so that its base is 3? Okay, and I know that 3 to the third power is the same as 27. Okay, I just rewrote the 27 as 3 to the third power. Here's where that property kicks in now. Note the bases are the same. They're both 3. So that's going to guarantee now, since it's an equation, I can just set the exponents equal to each other. Okay, so a lot of 3's in this problem, but 3 was the base, and then 3 happened to be part of the exponent. But we can go ahead and solve that for x now, just by dividing by, again, our number 3. So the answer to this equation would be x equals 1. Okay, and you can verify that, verify like usual if you want to be, extra sure, go ahead and plug that in. 3 to the 3 times 1 power, it should be 27, and it is. Okay. Okay, so let's set up another one here. Again, same kind of thing. We recognize it's an exponential. There's a variable built into the exponent somewhere. So let's see if we can rewrite the other side, the 256. Okay, does that equal 4 to some power that we can rewrite it as? And I think if you check 4 to the fourth power, okay, and sometimes you just have to use a calculator on these. If the numbers are big, just try and check it out. 4 times 4 times 4 times 4. Usually it won't be too big of a number because, you would just be checking forever. But in this case, 4 to the fourth. So we can use our little property again. Notice the bases are the same. I can go ahead and set the exponents equal to each other, okay, from our property a couple pages ago. Okay, so the 9 minus 2 has to be the same as 4, and if we solve that, we'll just add the 2 over, and then divide by 9. Okay, and we could reduce that down 2/3. Okay, so n would be 2/3. That'd be our solution there. Okay, this one, couple different things you should notice. First off, there's exponents on both sides, and they both have variables already. So this one could be a little bit trickier. But let's think about this. Let's look at those bases first. That's what I want to kind of focus on right now. The one base is 3, the other base is 9. Okay, and it should kind of jump out at you that you could rewrite 9 as 3 squared. Okay, so this side, let's leave the 3 alone here. The right side, 9 is really 3 squared. Okay, and that's still getting raised to a power. Okay, so the bases are the same. They're both 3. It's just that there's something going on where the right side has 2 exponents. So if we remember how to handle something like this, a power to another power, that's when you would multiply exponents. Okay, so the left side here is just 3 to the 5x. The right side, if we kind of distribute that 2, to both terms, this would really be 3 to the 2 times 2x, or 4x, and 2 times minus 1, it gets distributed. So a minus 2. So the right side's really 3 to the 4x minus 2. So we had to do a little trick, but now we got our thing that we wanted. The bases are the same, they're both 3. Let's go ahead and set the exponents equal. So 5x would equal 4x minus 2. And let's go ahead and solve that for x. We can subtract 4x from both sides. And we'll be left with 1x, which is what we want. X equals negative 2. Okay, and that would be your solution to that one. Okay, I believe this is the last one. There might be one more. But this one has another little wrinkle in it here. So the left side looks good. It's the right side, not so good. Okay. One thing to remember though, when you see a fraction, okay, especially if there's a 1 in the numerator, this is probably going to be something with a negative exponent. Okay, you know, a negative exponent makes you think reciprocal. So what I'm doing is I'm looking down here at this 8, and I know that 8, okay, again, looking at this base, I know that 8 is 2 to the third. Okay, so this problem, the right side really here is we have 2 to the 2x plus 3 on the left. On the right side, I have 1 over 2 to the third. Okay, so what that makes me think of again, like I said, is a negative exponent. Isn't 1 over 2 to the third really just the definition of 2 to the negative third? Right? Usually, we're more probably used to taking that and saying that it equals that. So we're just kind of going the other way. They're the same thing. They're equal to each other. So we can do that replacement in there, and that helps us with our conditions or the property that we want to use, because now both sides have the same base. Right? So now we have base of 2 on both sides. It just so happens that one of them is a negative exponent, but that's okay. So we can just set our exponents equal to each other. Sorry, I got a little sloppy with my erasing. That was negative 3, we said. So now we'll just set them equal. Okay, the exponent has to equal the other exponent. So 2x plus 3 needs to equal negative 3. And if we go ahead and subtract the 3 from both sides, 2x would equal negative 6. And then, of course, dividing by 2, we would get our answer of negative 3. Okay, and that's that. Now, let's see, is that the end? Yeah, so the assignment's going to be a worksheet. It's going to be a review, some graph problems, some of this new things here. And then we'll get to very soon, some of you might be thinking, you know, what if you can't rewrite it? You know, what if there was a problem like, you know, 2 to the x equals 10 or something? You know, there's really no way to rewrite 10 as 2 to some power, right? So it's going to be kind of hard, and we're not going to be able to do all the problems the way we did in this section. That's when we're going to use one of our new friends here called the logarithm. So that's what's coming up. Okay? All right.